Yeah, welcome back students to our last part of this course. Which will be presented to you as 15th lecture. Sorry, 16th lecture. Let me change this. Okay, in the first hour's class today, we dealt with an illustrative example to understand the Q learning function and how the values of Q estimations, that is Q cap as A, estimated value of Q evaluation function, Q cap SA, will tend to converge as you increase the number of iterations as n tends to infinity. Okay, these values will no longer change. When they doesn't change any longer, that is called as the point of convergence. And at that place, Q cap value will be almost equal to the value of regular Q learning function. Okay, Q cap is called as the estimation and Q is the original Q learning function that have to be learned. So after n iterations, where n is very large number, in that case, agent would have received sufficient amount of training in order to explore each and every path to reach its goal. Okay, in that case, the estimation of this Q evaluation function will almost be equal to Q. And in this last class, we are going to just see what would be the experimentation strategies that would be followed by an agent in order to learn better in its environment and how the updating sequence will be carried upon. Right. So notice the Q learning algorithm does not specify how actions are chosen by the agent. It doesn't tell how actions are chosen by the agent, but it tries to optimize how the actions are taken when starting from some initial state S1 or S2, randomly selected state. So one obvious strategy would be for the agent in state S, say some random state S taken, to select the action A that maximizes this estimated value, thereby exploiting its current approximation Q cap. So what would be the plan that is followed by the agent? The Q learning algorithm does not specify how actions are chosen. It will just try to exploit how a strategy is followed by the agent to reach its goal state. So the obvious strategy that can be followed by the agent in state S to select action A that maximizes this estimated Q value. So its ultimate goal would be to increase the accumulated reward points. Okay, by checking in various directions, in which way if it goes, it will accumulate more reward points, or in which way if it goes, it may have to encounter some penalization of the points. Based on that, it will move in a direction that maximizes its estimation, that is the accumulated reward points have to be maximized. Okay, that would be the best solution. That would be the best sequence of steps in order to move towards its goal. Okay, thereby exploiting its current approximation Q cap. Randomly, we start with some value, right? We start with some random reward values, but later they will be refined based on the agent's experience that it gains by exploring each and every state from a random initial state. Got it? Say if there is a grid like this, then the agent will start at a random state in one episode here, in the next episode here, in the next episode here, in the next episode here, and travels towards this goal G. And the steps taken, whether they are optimal or not, it can be calculated only by the sequence of steps it has taken and the reward points accumulated across that sequence of steps. Okay, so initially in the QCAP table, that is the Q function approximation table, we start with random values, and whenever it explores some path in an episode, that path's reward points are recorded, and this will be repeated number of times so that it will be able to decide which would be the optimal control policy later on. Okay, and that will not be the final again. If at all it encounters a new set of environment, the environment in which it is learning something, if it encounters an entirely new environment, then it may have to refine its QCAP value, though it is converged. Okay, so with this strategy, the agent runs this risk that it will overcommit to actions that are found during early training to have high QCAP values while failing to explore other actions that have even higher values. So what happens with this strategy? The strategy that is adopted by the agent to maximize its reward points, in that case, if at all it comes across some sequence of steps where it is encountering really high reward values, then it may avoid itself from exploring other sequence of steps where it can have even more good reward value points. Okay, so it is like overfitting. It is trying to overcommit to sequence of steps which accumulated it good number of reward points. That is one risk with this agent. If it encounters in the initial stages good sequence of steps, it will try to adjust with them by not exploring other sequence of steps where it may encounter still more good accumulation of reward points. Now, in fact, the convergence theorem above requires that each state action transition occur infinitely often. That is why what you're doing is you're not making that agent settle or overcommit to initial sequence of steps having good reward value points. What we are doing is we are making the agent learn again and again, irrespective of the reward points accumulated until QCAP converges to Q. Okay, so what we are doing is we are trying to make the agent go through state action transitions infinitely many times. Though it have started from this initial state, we are making it to start from that initial state many times, infinitely many times, so that it can explore all possible sequence of steps to reach the final goal state. Now, among them, whichever is the best sequence of steps can be selected later by the agent after QCAP reaches Q, after QCAP tends to the real value Q. Okay, so in fact, the convergence theorem above, that is what we discussed in the previous class, requires that each state action transition occurs infinitely often, occurs many number of times in the journey of the agent from the initial state to the final state. Now, this will clearly not occur if the agent always selects actions that maximize its current QCAP value. If the agent tries to maximize only its current QCAP values, then this agent may not tend to learn or explore other sequence of steps where it can encounter more accumulation of reward points. Okay, for this reason, it is common in Q learning to use a probabilistic approach to select the actions, to select the actions. Okay, so for this reason, in order to avoid the agent to overcommit to the initial best sequences of actions, it is common in Q learning to use a probabilistic approach. You know how probabilistic approach can be used in Bayes' theorem we have used, right? Bayes' probabilistic reasoning. You remember, we are attaching some confidence in order to make a statement or in order to formulate a hypothesis. Same notion or idea we are using here. Okay, it is common in Q learning to use a probabilistic approach to select the actions. What actions can be selected? This action is more probable. This action should be selected because it has higher likelihood. means it gives higher reward points in order to reach the final goal state. Okay, such kind of probabilistic approach can be attached to this Q learning approach. Actions with higher Q values are assigned higher probabilities, but every action is assigned a non-zero probability. Okay, action in different directions can be assigned a non-zero probability, means it should not be entirely zero, but some likelihood have to be assigned to it. Some chance have to be assigned to each of the actions, but actions with higher Q values are assigned higher probabilities. So where there is chance of accumulating more reward points, let more probability be assigned to it. Let more chance of that agent taking that particular action be assigned to it. Okay? That is what we mean by probabilistic approach. One way to assign such probabilities is, how to assign such probability? Probability of taking an action AI given the state, means to go from that state, move from that state by taking an action AI. How can it be represented? It is represented as a constant raised to the power of estimated Q cap value divided by adding all those constants raised to this Q cap value. Now, what is this constant? First of all, let us see. Probability of AI given S is the probability of selecting action AI given that the agent is in a particular state S. And what is K? The constant K, it is greater than 0. It should not be a negative value, which is a constant that determines how strongly the selection favors actions with high Q cap values. How strongly the selection favors. If you keep K value larger, it favors higher Q cap values. If you keep the K values lesser, then it favors lesser reward points. Okay, delayed reward points. So what is given here? Where K greater than 0 is a constant that determines how strongly the selection favors actions with high Q values. S has lots of actions that can be performed. It has different options that can be performed. Say S is here. Now it can go in this direction. It can take action in this direction, in this direction, in this direction. Say it has 4 choices to perform the action. Now, K is a constant that determines how strongly the selection favors action with high Q value. Say, if this Q value is high. If Q value that can be obtained is high, if the agent moves from this state by taking an action A3. This is A1, A2, and A4. Okay. Then what would be the strength in the selection of moving in this particular direction so that it can accumulate high Q cap values? Okay. That strength can be decided by this constant K. The larger values of K will assign higher probabilities to actions with above average Q cap. Okay, so if you want more reward values, more accumulated reward values than the average, then K has to be kept larger, causing the agent to exploit what it has learned and seek actions it believes will maximize its reward. So when you keep K, when you keep the constant K value larger, what do we mean by that? We want the agent to exploit what it has already learned. It will have a knowledge base, right? It would have stored in its memory. If it takes this action, what will happen? If this action, what reward can be obtained, right? So it can exploit what it has learned already and seek actions it believes will maximize its reward. Means it has some actions that are already performed from this particular state. Among those actions, which is having highest reward value, it can try to exploit that knowledge which is already existing. If we keep K value high, we are instructing the agent or we are guiding the agent to exploit the existing values. In contrast, small values of K, this constant K, will allow higher probabilities for other actions leading the agent to explore actions that do not currently have high QCAP values. Okay. What about lower QCAP values? Always if the agent is interested in higher QCAP values, higher accumulated reward values, what about the lower accumulated reward values? Remember, sometimes if the agent goes in that direction, it may come across a best sequence of actions than higher QCAP values already existing. In that case, it may lose that opportunity, right? That is why we wanted to explore that side of the learning also. If at all there are previous QCAP values which are lesser, by keeping K less, that is the constant we are using here, lesser, we are suggesting to the agent to explore the actions which are having lesser accumulated reward values. If it is going in that direction, maybe it may come across some optimal sequence of steps which are better than the already existing higher accumulated reward points. That is why if you keep K larger, we are asking it to use its previous knowledge about the highest reward accumulated values. But if you are keeping K value lesser, then we are asking it to explore QCAP values where they are lesser and see whether it can come across some better optimal control policy. Okay, that is what we mean by this. Now, in some cases, K is varied with the number of iterations so that the agent favors exploration during early stages of learning, then gradually shifts towards a strategy of exploitation. Very nicely explained in this step. See here carefully. Why do we vary this K, the constant K? Initially, if you want to make the agent learn from its previous knowledge, keep the K higher. But if you want to gradually shift towards a strategy of initial stages, it can be learning, that is exploration. I'm really sorry. Initial stages, when you keep K value lesser, then we are making it to learn first. Okay, now it will gather some knowledge by learning in the initial stages. Means it will explore lots of sequence of steps to reach the final goal. It will explore, say, some 4 sequence of steps to reach the final goal from different states, S1, S2, S3 and S4. Okay, now in the initial stages, when you keep the K value lesser, then it will start learning the control strategies to maximize QCAP. That is accumulation of reward values. Now, because sufficient number of values are accumulated, sufficient number of sequence of steps are accumulated, sufficient number of plans here are accumulated by the agent to move towards the goal state. Later, you can keep increasing K so that you can move your strategy, shift your strategy towards exploitation. Means hereafter, rather than exploring new ways to reach the final goal, use its existing knowledge and select the strategy or select the sequence of steps where the QCAP value is more. That is where the accumulated reward values are more. Okay, so there should be a trade-off that have to be maintained between exploration and exploitation. That depends on the machine learning expert to make that trade-off. How far the agent have to first explore the learning so that it records all the sequence of steps to reach the final goal and then start exploiting. That is, use its previous knowledge in order to select the optimal control policy to reach the final goal. Got it? So one important implication of the above convergence theorem, what we have discussed, is that Q-learning need to train an optimal action sequences in order to converge to the optimal policy. Okay, this is an implication. This is like one restriction in order to make the Q-learning converge to an optimal control policy. But it can learn the Q function and hence the optimal control policy while training from actions chosen completely at random at each step, as long as the resulting training sequence visits every state action transition infinitely often. So we are making the agent to start at random positions, start at random states, and then do the same operation many times until this Q cap function converges to Q. This fact suggests changing the sequence of training example transitions in order to improve training efficiency without endangering the final convergence. So what does this state us? What does this suggest us? Let us change the sequence of training example transitions in order to improve training efficiency. We want to improve the training efficiency by changing the sequence of training example transitions, changing the sequence of steps it takes to reach the final goal, but at a condition without endangering final convergence. Final convergence should not be endangered. You should not take completely different, complete deviation from the existing possible optimal steps. Okay, some steps are really optimal and the agent already learned about that. Now there is no use in deviating it to entirely different direction, right? That is what we mean. To illustrate, consider again learning in an Markov decision process scenario with a single absorbing goal state. Let us take a single absorbing goal state. Let us take a grid world example again. Say there is only a single goal state for this system. Now assume as before that we train the agent with a sequence of episodes. What do we mean by episode? For one episode will have the starting state, sequence of actions it takes to reach the final state. Every episode will have the sequence of steps followed by the agent from a particular initial state to reach the final goal state. Okay, so all these episodes will be stored in the memory of the agent in order to take a decision to make a particular move to reach the goal state in a given environment with a given initial state. Okay, now for each episode that is already in the memory of the agent is placed in a random initial state. What we are doing for every episode to train it, we are placing it in a random initial state and is allowed to perform actions. It will perform some actions to update its QCAP table. The table has for every state action, it has what would be the reward that can be accumulated. Okay, that is QCAP table. That is called as QCAP table with state A and with state S and action A. Okay, and to update its QCAP table until it reaches the goal state. So every episode what it does, it starts from a random initial state and counts the rewards accumulated across the sequence of steps it takes to reach the final state. That will be entered into this QCAP table. Now a new training episode is then begun. Now let us assume that a new training episode, we started a new iteration of training for the agent, is then begun by removing the agent from the goal state and placing it at a random new initial state. Okay, say initially it started with S1. Now let us, and it has reached, the agent has started from S1 and it has reached G. Now in the next episode, let us put it at some random state S2 and make it to reach the final goal. On the way, accumulating the reward points, which would be QCAP. Okay, QCAP of S8. That is starting from state S2, taking some set of sequence of actions A. It has reached the goal state G. Okay, such new training episode is begun by removing the agent from the previous goal state G and placing it at a new random initial state, now S2 in this case. Now if we begin with all QCAP values initialized to 0 or some random values, then after the first full episode only one entry in the agent's QCAP table will have been changed because it will take one sequence of actions, right from initial state to the final goal state. So only one QCAP table entry will be updated for that particular initial state. So the entry, that is the entry corresponding to the final transition into the goal state. Got it? So when it is starting from this state, what is the sequence of actions it has taken to reach the goal state, and what are the reward points accumulated on the way? And when it starts from S2, for one episode, it will make only one updation, right? The reward points accumulated on the path. Again, in the next iteration, for another episode, it can accumulate the points, it can get the points, sum of points accumulated when it moves from S2 towards the goal state G. Okay, and that will be taken as the second episode's QCAP value. So as many episode trainings are performed for the agent, those many updations will happen to the QCAP table. Initially, when it tracks through one sequence of actions, once the QCAP value will be updated. If the agent happens to follow the same sequence of actions from the same random initial state, we didn't forbid or we didn't restrict the agent not to start at the same same initial state, right? It can infinitely many times start from the same initial state again and again, because on the way the steps taken will be different. Lots of combinations are available to reach the goal state, right? So if the agent happens to follow the same sequence of actions from the same random initial state in its second full episode, if at all that is the scenario, again same initial state and same sequence of actions it takes from that initial state, then a second table entry would be made non-zero, and so on. Now again second table entry will be updated. Again, if this iteration happens, third table entry will be updated. Okay, this updations happens again and again iteratively until it reaches point of convergence, and those iterations would be sometimes infinite. Why? Because it has to learn every possible sequence of actions within the environment given to it, within which the agent is within the environment in which the agent is learning. Okay, so if we run repeated identical episodes in this fashion, the frontier of non-zero QCAP, means the boundary value of non-zero QCAP values, will creep backwards. It will start moving backwards, propagating backwards from the goal state at the rate of one new state action transition per episode. Got it? So whenever we run repeated identical episodes, same episodes we are running, then the agent might have learned what reward it can get by taking a specific sequence of actions. So that knowledge will creep backwards, will be propagated backwards from the goal state at the rate of one new action transition, or one new state action transition per episode. Okay, so as you repeat the same episode underlying values, means you take the same initial state and same sequence of steps, then the reward points that would be encountered by the agent will be stored in its memory already. So that value can be propagated backwards to make the updation of QCAP more knowledgeable, okay, more informed. Now consider training on this same state action transitions, but in reverse chronological order for each episode. Means rather than going from initial state to the final state, let us move backwards, reverse chronological order for each episode. That is, we try to apply the same update rule for each transition considered, but perform these updates in the reverse order. Reverse chronological order means starting from end to the beginning. In this case, after the first full episode, the agent will have updated its QCAP estimate for every transition along the path it took to the goal. Okay, so the agent will have all the updated values of QCAP for every transition along its path from initial state to the final state, to the goal state. Now this training process will clearly converge in fewer iterations, although it requires that the agent use more memory to store the entire episode before beginning of the training for that episode. what is happening here is all its steps from beginning till the end are already stored. Now, if we try to if we try to apply the same update rule in the reverse chronological order, then the point of convergence will be reached very fast, because the agent already have the idea of previous rewards that are given to it in the beginning of the episode. Now, once it has learned all the rewards that it can encounter by taking a sequence of steps, when we are training it in the reverse chronological order, you can propagate all these rewards that are encountered backwards, so that the agent will get an immediate reward. It will know what kind of reward it can get for taking a specific action, so that it can select only the optimal steps. Another strategy for improving the rate of convergence is to store past state action transitions along with the immediate reward that was received and retrain on them periodically. Okay, so whenever an action is taken, some reward will be given to it, store it, and try to train it again and again at frequent intervals of time, so that it will be used to that actions which would get only optimal rewards, only highest rewards. Although at first it might seem a waste of effort to retrain on the same transition, because we are training the agent on the same transition again and again, so that it remembers well what would be the rewards that it can accumulate in order to maximize the final reward points. Okay, though it is waste of effort to retrain the same transition, recall that the updated Q estimation value is determined by the values Q cap S dash of A, S dash A. What is S dash? The next state. S is the current state, and it is moving to a next state S dash by taking an action A. So what is the value in the next step? This Q cap S of A is determined only by its next state, right, of the successor state S dash, which can be represented as delta, the change in the agent by moving from state S by taking an action A. Okay, now the updated value Q cap of SA is determined by the value of its next state, that is its successor state. You remember in MTP, the successor state is determined by its immediately previous state, right? Same thing we are using here. Instead, when we wanted to update Q cap, it is determined by the values that it goes into, to the state it goes into by taking action A. Therefore, if subsequent training changes one of these Q cap values, then retraining on the transition from S by taking an action A may result in an altered value for Q cap of SA. So when you keep on training again and again in various iterations, as you know the next state, it is easy to estimate its previous state, that is Q cap. Once S dash A is known, Q cap S dash A is known. Okay, so if you keep on, say, you are trained to drive across a road, on a road, okay, in your first training class. Then in your second training class, your work will become more easier. In your third training class on the same road, because you know what would come next, a speed bump would come, speed breaker would come, or a pit hole, some hole would come on the road, because you will be trained about the environment in your previous episodes. In your third episode, you will be more skillful, and in your fourth episode you will be more skillful, so that you get good rewards from your coach. Same thing happens here. If it is trained repeatedly again and again on the same sequence of steps, it will know which action will be rewarded and which action will be penalized. That will help it to increase the estimate of Q cap and quickly converge to the original value Q. So in general, the degree to which we wish to replay old transitions versus obtain new ones from the environment depends on the relative cost of these two operations in the specific problem domain. Okay, now if at all an agent comes across a specific situation. Now, at that situation, what action it has to take? Now, exploring that action, if it is too costly, it will tend to exploit its existing knowledge about taking that step. Did you understand? If at all the cost involved in taking a new step, if at all the risk involved in taking a new step and exploring that, then it will try to use its previous knowledge at this particular step or at this particular state. What would be the best step to take, best action to take to go to the next state? Okay, so it will take its knowledge base, gets the knowledge from that and takes that step, because there is much risk involved in exploring the new step, exploring the new action. Okay, so the degree to which we wish to replay old transitions versus obtain new ones from the environment depends on the relative costs of these two operations. Wherever the cost is lesser, it will try to go in that direction. We can program it to go in that direction, in that specific problem domain. Okay, say if the risk is lesser in exploring a new path rather than using its older knowledge, then it will obviously will suggest it to proceed with the exploration strategy only, not the exploitation strategy. For example, in a robot domain with navigation actions that might take several seconds to perform. This example is quite clear to explain you this concept. In a robot domain with navigation actions that might take several seconds to perform, the delay in collecting a new state action transition from the external world might be several orders of magnitude more costly. Say, if a robot is driving on a road, now it has to take some action in order to move from this state to the next state. In that case, in the real time, it is very costly to explore that action. In that case, it will simulate the same environment internally and try to see what would be the rewards that it can accumulate. And based on that feedback, if it is rewarded for that simulated action, it will perform the same action in the real time. But if it is penalized for that simulated action, then it will stop or it will avoid doing that action in the real time. And it will try to exploit some other action from that current state. So what is happening here? Because it has to encounter larger cost to take some exploring action, to perform some exploring action, or to follow an exploring strategy, it simulates that entire environment within itself and understands whether a particular action will be rewarded or penalized. And based on that knowledge, it will, based on the knowledge of its simulation, it will take the next step. Got it? That is how a trade-off is maintained, to use the existing knowledge of the agent or to gain new knowledge, of that for that agent. Okay, and now I'll read this, you'll understand. For example, in a robot domain with navigation actions that might take several seconds to perform, the delay in collecting a new state action transition from the external world might be several orders of magnitude more costly. It is not able to compromise with that. It is too costly in order to perform a state action transition, because it is taking too much time, not only in terms of the cost is measured in terms of time. If it is taking too much time for an autonomous driving vehicle to take the decision to drive forward, then avoid that step. The agent will avoid that step and it will simulate the environment internally, and it will gain and it will select the best move which is highly rewarded by the environment, and same thing it will apply in the real time also. Okay, so with respect to time, with respect to efficiency, with respect to risk, it will try to measure what would be the risk involved, what would be the time taken for taking a particular action. If it is too high, it will use its existing knowledge to perform that step or to move forward. Okay. This difference can be very significant given that Q learning can often require thousands of training iterations to converge, right? So this difference, whether to explore or exploit, can be very significant given that Q function learning can often require thousands of training iterations to converge, right? In order to make the agent perform very well in the environment, it has to be trained repeatedly again and again until the accumulated reward point values estimation of that is equal to the original Q function value. Now note, throughout the discussion, we have kept our assumption that the agent does not know the state transition delta. Means the change that happens to the agent to move from state S by taking an action A delta, okay, used by the environment to create the successor state S dash. S dash is what? Next state is nothing but the change in the current state by taking an action A. I'm repeating, S dash is the next state, that is nothing but change delta in the current state S by taking an action A. Okay, now so far we have assumed that we doesn't know delta. What would be the change? It is just taking a step, or the function R of SA, that is the reward used, the reward points that can be accumulated. Means we doesn't know what change it can bring in the environment, and we doesn't know what kind of reward it encounters by taking a specific action a priori. Previously we don't know until an action is taken. If it does, but so far we have assumed like this. That is why we have established a Q evaluation function in order to work in such environments where delta and R are not known. But if at all we know these two values prior, maybe after repeated training of the agent, if it does know these two functions, delta and R, that is the change in the state and the reward that it can encounter due to change in that state by taking action A, then many more efficient methods are possible. If we have more knowledge about the underlying parameters, then we can design more efficient methods, right? So for example, if performing external actions is expensive, the agent may simply ignore the environment. As I said already, if at all the robo understands that performing external actions is expensive, and it may simply ignore that environment and instead simulate it internally within itself, within its knowledge that is acquired, from the knowledge that is acquired, efficiently generating simulated actions for that particular environment that is simulated. What are the possible set of actions that are appropriate, and assigning the appropriate simulated rewards. Now, when such action is taken, what would be the reward that it can encounter? When some another action is taken, simulated action is taken, then what would be the simulated reward it can encounter? Now, among those, whichever action has the highest simulated reward, that action will be automatically selected by the agent, and it performs that action in the real time. Okay, so a large number of efficient algorithms from the field of dynamic programming can be applied when the functions delta and R are known. Okay, in this case, in robot learning newly, this R and delta may not be known in the initial stages, but once it is rigorously trained infinitely, and Q cap tends to be similar to Q learning function. At that point of time, maybe we can immediately estimate delta and R before some action can be taken. And at that point of time, we can still implement, we can take up more number of efficient algorithms from the field of dynamic programming, which can be applied in this scenario where delta and R are known prior to taking the action. Okay, we completed our course now. with this topic, but I just wanted you to happily end this by answering these few questions, simple questions. What is S and A in the context of reinforcement learning? What is S, students? What is S and A we have been using so far? S is set of what? Are you there on the other end, students? What is S? Set of states or actions? Set of states from which the agent have to proceed further by taking set of what? A. What is A? Set of?
Set of actions.
Yes. Yes, good. Set of actions. An agent have to move from a current state S by taking an action A. When it will be given R. What is this R? What is R? When an agent moves from state S by taking an action A, it will be given R. What is that R? It will be given some positive feedback, right? What we call that? Yes, very good. Reward. R is the reward given for the agent for moving from state S by taking an action A. That reward, if it is positive, it is a positive feedback. But if it is given negative values, then it is a negative feedback, which is not anticipated. So what should be the final goal of the agent? To accumulate more and more number of positive points, to accumulate more and more number of rewards. Okay, so that will be the best sequence of steps it can follow to perform its task or to reach its final goal. What is R of SA? Can you read this? Instead of saying simply R of SA, can you read it more elaborately? Any of you? R of SA, we can read it as reward that is encountered by the agent for moving from state S by taking an action A. I'm repeating again. R of SA can be read as the reward that is accumulated or encountered or gathered or obtained by the agent for moving from state S by taking an action A. Okay. Now what is V star? You remember? V star is the highest reward accumulation, highest value of rewards that are accumulated by the agent. Say it has taken step 1, it is given some reward 90. Now it has taken step 2, it is given reward 80. Now it has taken step 3, it is given the reward 100. Now again in another episode, it has taken step 1, it is given reward 80. It has taken step 2, it is given reward 100. Step 2, it is given reward 100, and it takes step 3, it is given reward 100. Now in which sequence of steps V star is more? V is more in this second sequence of step, right? It is 280. So here the rewards accumulated is more. Accumulated means added up, that are collecting, that are collected by the agent by taking that sequence of steps. Okay, so V is called as the accumulated reward points, and V star is called as the highest accumulation of reward points by following the optimal control policy. Pi is represented as the control policy, that is the sequence of steps an agent follows from its initial state to reach the final state or to perform a task in an anticipated way, in a desired way. Okay, the policy followed by it is called as control policy, and that is pi. But if that control policy is optimal, means making that agent perform the task very efficiently, then we call it as optimal control policy, which is indicated by pi star. Got it? So this is how we end this course successfully. But I want all the students to go through the videos repeatedly to get the concept, because all these concepts involve a lot of mathematical concepts. All these topics involve a lot of mathematical concepts, and they're very complex enough for us, right? But as PG students, it is not very difficult for you to understand if at all you keep some sustained effort to learn. So go through the videos repeatedly until you understand the topic, and I'll always be available until 11 o'clock in the evening over WhatsApp. You can message me your doubts. I'll try to answer you. Okay, so from next week we'll start revision sessions. If those sessions are interactive, it would be better, because your doubts will help even other students to get their doubts clarified. So make the sessions interactive for a positive learning environment. Okay, students? So I expect more attendance from next week for the revision classes also, as we are doing now. Right? We'll meet next week. Happy Christmas to all of you.
Same to you.
Same to you, ma'am. Thank you.
Thank you. Enjoy the holiday. Bye.
Bye, ma'am.